So today we're going to talk about the inference rules for identity in the predicate calculus. There's two of them, identity introduction and identity elimination. So just to review a little bit about identity, we've already adopted the equal symbol into predicate logic and we've assigned it a specific meaning. It's a two-place relation, meaning identical to, which is exactly the meaning we're familiar with from arithmetic. Remember that in logic, identity, like the other relations, holds between names and variables, but not predicates or entire proposition. So we never write things like P equals Q or F of A equals G of B. Those are nonsensical. So although identity is just a relation, it's a special one. And one way we emphasize this is by placing it between names and variables rather than in front. So if we had wanted to, we could have chosen to write it like that, but we don't. So we can say A equals B, or for all x there exists a y, x equals y, or for all x, if f of x, then x equals b. So this is all stuff you know. So there are two inference rules for identity. The first rule is identity introduction, and it's very simple. Identity introduction just says that if you have any name, A, B, C, D, whatever, you can introduce the identity, A equals A, or B equals B, or C equals C. So the justification for this rule is simply identity introduction. That's all that we write. There's no line number to cite because it's not an operation on a particular formula. You can even introduce it at the beginning of a proof if you like. And we'll see this momentarily. So there's not a lot of interesting stuff that you can prove simply by adding identity introduction to the predicate calculus. But you can prove what we call the reflexivity of identity, which is simply the theorem that everything is identical to itself. In fact, the reason we adopt identity introduction as a rule is because of the reflexivity of identity. So how do we prove it? Well, we just start out by saying that we're going to show that for all x, x equals x. And on the very first line, we can simply introduce, through identity introduction, some identity. I chose C, it could have been anything. C equals C, and then we just do a universal introduction on 1, and Bob's your uncle. Why can we do that on 2? Because on line 1, even though C equals C occurs above, it's not in an assumption. Okay, so very simple proof using the reflexivity of identity. So the second rule, identity elimination, gives us a little bit more power. This rule allows you to substitute identical expressions for each other. So for example, if we know that A equals B, and we know that f of A, we can conclude that f of B by just substituting A for B in f of A. So identity elimination is defined in this way: for any names A and B, if you have somewhere on a line that A equals B, we may substitute A for any occurrence of B, or alternatively B for any occurrence of A. So the justification for identity elimination involves two lines. The first is the original identity statement, and then the second is the line in which we are making the substitution. So note that this is an inference rule. It's not an equivalence, so we don't perform this substitution on subwoofs within a formula. So let's prove the symmetry of identity. So what is symmetry? Well, to say that a two-place relation is symmetric is to say that if it holds between two things in one direction or one order, then it necessarily holds between them in the reverse order as well. For example, sister of is a symmetric relation because if Jan is a sister of Anna, then Anna is necessarily a sister of Jan. So we can prove that identity is a symmetric relation as well. And the way we would prove it is to prove this as a theorem. For all x and for all y, if x equals y, then y must equal x. So how would we do this? Well, the method is something familiar to you already. We see that we have a universally quantified statement that's a conditional. So what we're going to do is assume or hypothesize the antecedent of the conditional using names, and then try to derive the consequent, and then slap on two universal introductions at the end. So we will hypothesize that A equals B. We haven't used the rule of identity here, either of the rules. We've just hypothesized that A equals B. But then, having hypothesized A equals B, we want to get that B equals A. Because if we can show that if A equals B, then B equals A, then we've basically achieved our objective. All we have to do is do two universal introductions. So how are we going to do that? Well, we're going to introduce A equals A. We could also have introduced B equals B. It'll work either way. So now that we have A equals B on line 1, and we know by identity introduction that A equals A, what can we do? Well, remember that what we're trying to get is that B equals A. So what we want to do is substitute B into A using identity elimination. So by lines 1 and 2, we can have B equals A by identity elimination. That gives us our conditional introduction proof, and then two operations of universal introduction, and we're done. So identity is also what we call a transitive relation. So what does it mean for a relation to be transitive? Well, we say that a relation like sister of is transitive because if Anna is a sister of Jan and Jan is a sister of Mel, then Anna is a sister of Mel. Now, not all relations are transitive, but there are a lot that are. For example, bigger than, inside of, east of, implies, etc. So let's prove the transitivity of identity. So what we want to do, what that amounts to is proving this theorem. Let's prove that for all x, for all y, and for all z, if x equals y and y equals z, then y equals z. Now I'm sure you can do this. It's going to proceed in almost exactly the same way as the previous proof. So take a whack at it. So we're going to hypothesize that A equals B and B equals C. And now what we want to derive is A equals C. So let's go ahead and separate A equals B and B equals C using and elimination. And then we can see, just by looking at these two lines, that since A equals B and B equals C, then we can get that A equals C by substituting A into B by identity elimination. Okay? And so that gives us our conditional introduction proof, and then once again we have now three universal introductions. Well, here's something that might be interesting to think about. Consider this argument. Bo is not Joe. Joe is not Mo. Therefore, Bo is not Mo. Is this a valid argument? Sounds kind of valid-y. Let's look and see, though. Let's see if we can prove it. Let's prove that if it's not the case that Bo is identical to Joe, and it's not the case that Joe is identical to Mo, then it's not the case that Bo is identical to Mo. So we're going to we have two assumptions, and we want to derive that it's not the case that Bo is identical to Mo. So let's do this. It's not the case that Bo is identical to Mo. 1, 2, identity elimination. Is that a good move? Are we done? Well, no, this isn't right. It's not right because the rule of identity elimination only allows you to substitute into identity statements, not negated identity statements. So, is this a valid argument that we can't prove? Well, actually, no, it's not valid. If you think about it, it's not too hard to provide a counterexample. For example, Superman is not Lois Lane. Lois Lane is not Clark Kent. Therefore, Superman is not Clark Kent, but he is, right? So that would be a very poor inference, and that's just something we don't want to be able to prove. So let's try to prove this. Albert is happy. Corey is wealthy. Nobody who is wealthy is happy. So clearly, Corey is not Albert. Does that sound right? Albert is happy. Corey is wealthy. Nobody who is wealthy is happy. So clearly, Corey and Albert are not the same person. So Albert is happy. Corey is wealthy. For all x, if x is wealthy, then it's not the case that x is happy. We want to show that Corey is not Albert. Okay, so let's see if we can do it. We get from assumption 3, a universal elimination, and we could go to either C or we could go to A. Okay, so if we go to C, if Corey is wealthy, then it's not the case that Corey is healthy, is happy. What does that allow us to do? Well, it allows us to generate by conditional elimination that it's not the case that Corey is happy. Well, how would we go on from there? Well, we're trying to show that it's not the case that Corey is Albert. So, if we assume that he is through a hypothesis for negation introduction, can you see how that would generate any interesting results? Well, now we have that C equals A, and we have HA, and we also have not HC. So this is going to allow us to substitute either A for C or C for A. So take your pick. We can have it's not the case that HA by 5, 6 equals elimination. What have we done here? Well, we have just taken our identity and we've substituted A for C, and that's given us not HA. But of course that gives us the contradiction that we're looking for. So by 1 and 7 contradiction, we have the contradiction we need to get out of this proof. And it's not the case that C equals A is the result we're looking for. Let's look at another one. Matilda is dancing with Sabine. So either someone is dancing with herself or Matilda is not Sabine. Matilda is not identical to Sabine. So Matilda is dancing with Sabine. It follows, therefore, that either someone is dancing with herself or Matilda and Sabine are not the same person. So for simplicity, let's just go ahead and assume that our universe only contains people and that gender is irrelevant. So Matilda is dancing with Sabine, capital DMS. Either someone is dancing with herself or Matilda is not Sabine. There exists an X such that DXX or it's not the case that m equals s. All right, can you prove that? Give it a shot. Okay, so we have only one assumption, DMS, and we're trying to prove a disjunction. Now you'll remember that when we try to prove a disjunction, there's a couple ways to go about it. One way is to try to just get one of the disjuncts. The other one is to think of the disjunction as a conditional and use material implication to prove the conditional, and just, use conditional introduction to prove the conditional, and then material implication to convert it back into a disjunction. So we know that there exists an x dxx, or not m equals s, is the same as saying if it's not the case that there exists an x dxx, then it's not the case that m equals s. So that would suggest that we hypothesize that it's not the case that there exists an x dxx, and try to derive not m equals s. So is there an obvious way to do that? Well, an obvious thing to do is to apply the quantifier exchange rule to number 2 to get a universally quantified statement for all x not dxx. It's not obvious what we're going to do with that right now, but remember that since we're doing a conditional introduction, we're trying to derive it's not the case that m equals s, and so it's open to us to proceed with the negation introduction by assuming or hypothesizing the opposite of m equals s. So what if we were to do that? Hypothesize that it's not the case that m equals s, and try to derive a contradiction. Well, if we hypothesize now that m equals s, then if it's not the case that dxx, then we know that it's not the case that dmm, and we also know that it's not the case that dss. Both of those are available to us by universal elimination, and it looks like then we would be able to use identity elimination to create a contradiction with the first assumption, the only assumption. So what if we went ahead and wrote DSS by 1 for identity elimination, right? So now we're just taking our assumption DMS and substituting S in for M to get DSS. But now from line 3, we know that for all x, it's not the case that dxx, right? So we know specifically that not DSS, and that's our contradiction, right? So we can just write P and not P by the contradiction rule, 5-6 contradiction, and we're pretty much all the way home, right? Because now we can assert it's not the case that m equals s by 4 through 7 negation introduction, and as a result we can assert that it's not the case. If it's not the case that there exists an x dxx, then it's not the case that m equals s by conditional introduction. Now of course that's not what we wanted to prove, but through material introduction we can demonstrate that it's not the case that there exists an x dxx or not m equals s, and finally by double negation we can have our result. Okay, so a lot of power comes to us. Things we just could not prove at all, we can now prove using these two rules. So let's do one last one. Okay, so let's prove this is a theorem. Nothing has nothing that is identical to it. What does that actually mean? Nothing has nothing that is identical to it. So there is nothing such that nothing at all is identical to it. So that's just really a way of saying that everything has something that's identical to it, but we'll prove it in its negated form. So it's not the case that there exists an x such that for all y, it's not the case that x equals y. So how are we going to prove this? Think about it a little bit. I think it's going to come to you pretty quickly. So what we're going to do is proceed by negation introduction and assume that there does exist an x such that for all y it's not the case that x equals y. And of course this is going to immediately land us in an existential elimination hypothesis. So we've got two hypotheses back to back. So now we're saying that for all y it's not the case that a equals y. Now what are we going to do here? Well, you just have to think a little bit, right? I mean, this is a universally quantified formula, and so you can do a universal elimination to anything you want. That means you can go to A, to B, to C. What would it make sense to go to? Well, clearly, it would be a really good idea, since we're looking ultimately for a contradiction, to go to it's not the case that A equals A, right? And why is that? Well, because we know that A does equal A by our handy identity introduction. There's our contradiction. So we say P and not P. We punch out of the existential elimination proof in the customary way. And notice it was important here, actually important for us to use P and not P, because if we had used A is in the hypothesis, and that's not okay. But now we have our contradiction, and so that allows us to assert the negation of the hypothesis. All right, so that's how the two rules for identity work, and now you just want to hang in there and work through these study questions.